the steps of encapsulation. So again, Bob, the user, uses an application, and the application creates data. And if he wants to ship that to another user, to Alice, he's going to have to address it to her. So you're just writing an envelope. You're going to say, Alice has her own computer. And her apps. So from this application to that application, from the web browser to the web server. And you address that in a segment header. I should have made that green. I like to keep my green, keep it consistent. Applications are green, OSs are blue. You pick a port number and you go to the well-known destination number typically. So let's say the destination number, I'll pick an easy one, is 80. I am probably going where? What is that? What one's at port 80? Probably a website. Yeah, probably a website. A public facing, because internally you might want to change numbers. Who knows? Anything can run over anything. In fact, they do covert channels that way, running things and things you wouldn't expect. All right, but what's the source port? What would a source address be? Source port would be what? Anybody know? It's randomly generated, but it can't be, well, there's 16 bits in the field for port numbers. So that's 65,000 ports. You can't have a port 0. Ports 1 through 1023 are assigned, and you need kernel level access to even open them up. They are privileged ports. So port 80, that's assigned to web, and your client's never going to pick that. They can pick anything above 1023. Something greater than 1023. And then you can't just say to port 80. Port 80 where? Port 80 on their web server. So now I'll get back my blue. And I go, whatever, at 10.1.1.1, whatever your address is. And that's in the packet header. So we have port numbers go in segment headers, IP addresses go in packet headers, and that's all the information you need to logically send something to somebody. We call this the circuit level. Should be a C up there, sorry. Circuit. When I know the IP and port, when I say, you know, my whatever 10.1.1.1:80, oops, that's a socket. And it identifies, sockets identify the circuit that I need to get to. We're going to take a step back for a second. Picture what people do when they do intrusion detection a lot today, or any type of network analysis. With SSL and SSH, this is usually encrypted. I can't see what's going on here. Very rarely do I see clear text apps anymore. There was a time, shoot, when just about everything was clear text. Your mail was POP3 or SMTP. I could read all that, but they're run over SSL today. When I do network analysis, I am mostly looking at this information. That's how a circuit level firewall would work. But if I were sending IP import, yep. If somebody was sending this, now there should be a data header right here that if it's port 80, I would expect an HTML header. If it was mail, I would expect an SMTP header. Now inside your company, it might be in clear text, but externally it's generally encrypted. Application layer firewalls can inspect the headers if they're not encrypted. All right, but when it gets, remember, Bob's not on the same network as her necessarily. She could be around the world. There's going to be routers. There's going to be firewalls, the internet, whatever. There's going to be all kinds of things, access points. Your Ethernet only knows how to talk to Ethernet. So you're going to send to the nearest gateway, strips off the frame, rebuilds it for the next one, rebuilds it for the next one. Frames don't go over the internet. That's a local thing. Your MAC address. So mostly when we look at internet security, IDSs, IPSs, firewalls, they're looking at the packet and segment header at least. And if the data is unencrypted, they can look at protocol commands. Now, application layer firewall is not going to read the mail and make sure the mail is good. I would need some other content inspection engine to do deep packet inspection. You could do that on your IDSs. You could do deep packet inspection if it's clear text. But the more you look at, the slower it becomes. This is what I see on my sniffer. I've got the segment header that has the source and destination port numbers. Oh, 43 is a destination port. Who is that server, probably? There are a couple port number questions on the test, by the way. What typically runs at 443? HTTPS. Now, mail is typically at 25. Here's my my network layer, my source and destination IP addresses. And these make up the socket, the circuit. This is local. So this is the IP address of the server I was going to, like Google. This is the destination MAC address of my local access point here. These are the information in these headers. So when I go to a server, when I say www.google.com, the destination IP address, well, actually, when I say www, my browser immediately says port 80. When I got there on port 80, they said, no, this is SSL. You got to come back on 443. Oh, okay. All right. So I did that on 443. So my DNS told me, when I said google.com, DNS told me, oh, you want to go to this IP address. And the fact that it's SSL, we got to go to 443. And this is the IP address of the server I'm going to. This is the port number they're listening on. That's not their MAC address. All right, so at a very simple level, imagine there's only a few hops between me and Google. There's some routers in here. These are routers. My access point. Okay. Google. We say I like port numbers to be, so 443, that's them listening on 443. That's, source port over here, that's my browser. That's them. IP address, like that blue. Oh, this has already had blue, I'll pick black. Destination IP address, that's this machine. That if identifies that machine. Source IP address, that's me. Source MAC address, that's my network interface card. Destination MAC address, it's my access point. Access point rips it off, rebuilds it. Source MAC, destination MAC. Source MAC, destination MAC. Source MAC, destination. Why are the ports also in parentheses? Probably because I turned off naming. Double check that. I do typically turn it off, though I reinstall things so much. So let me erase that. And I turned off transport names. If I turn it on, and now it says HTTPS. My problem with names is source ports are high, but a lot of applications have, because we ran out of 1023, so people put stuff in high ports in now, and it might think my high port is some Aruba server. And I go, no, that's not it. No, that's just my local port. So I actually turn it off. I find it annoying. If you don't know that 443 is HTML, you need to get back to basics there. So I turn off transport names. Cool. I'm glad you enjoy it, Rev. Awesome. You know, I'm a show me guy, and this is why I love to sniff packets. I found in the very early in my career that a lot of things just seemed opinions, and I seemed stupid because I didn't have the opinion. But me, I was like, I can see stuff, and you know, packet sniffing is not an opinion. Either you were reading it right or you're reading it wrong. Now, you can only speak matter of factly about what you measure, and keep in mind, you can't measure all things. You can't measure get all. You're not going to get all the packets, not at all. Oh, could I illustrate that again? Sure. I'll do it in black this time so then I can maintain my colors. So again, my workstation, let me get a little bit bigger, is going to communicate to Google, and I'm going over the internet, right? Obviously, Google. So we've got my access point here. I've got to talk to, which is going to talk to my ISP's router somewhere. It's going to get me on the internet. And then there's routers all through the internet. That's what the internet is, you know, a bunch of routers and stuff. To their ISP's router, to their perimeter router, whatever. They probably have internal firewalls and external firewalls as well, but you know, very simple level. And I'm going to be going to their, I need to know their operating system, which you like to do in blue, the OS, my OS. They have an an application. Applications have port numbers, right? When they're apps, let's just say it's an app. To my browser, which is an app. But I don't just have that. I also have a network interface card. I have a physical interface. I have a NIC. A NIC. And they have a NIC, a network interface card. The addresses we look at are the NIC, the Ethernet interface, the network interface card. These are 48-bit addresses. Here's mine, right here. We have IP addresses at layer 3. And this is my IP address. And we have port numbers for TCP. And here's my port number. Yeah. So I go www.google.com. Well, DNS tells me, oh, google.com is at this IP address. So I know how to put this IP address in my destination packet. And I go, okay, I'm going to talk to you. Now I'm talking to the machine. But what app? They could have multiple apps running. The one that's on port 443. And this refers to this app. So again, this destination is Google. This destination is Google. My destination IP and port numbers don't change much. Now, you could have network address translation and stuff like that, port address translation. I'm just saying at a high level, that's not what's going on. But what is going on is the MAC address. This is mine, source MAC, but this destination MAC of here is not Google's. That's my access point. That goes here. And they strip the MAC header off. And now source MAC address, destination MAC, source MAC, destination MAC. MAC addresses, these layer 2 addresses, are locally significant. They only make sense on your local network, but IP and port number are globally significant. They're true around the world. Source MAC is the network access point and destination. No, source is me. Source MAC address right here, this source MAC address, this alpha, refers to my network interface card. So each router has a MAC address. Absolutely. Absolutely. Every router has to have a MAC address. Yeah, because the router is not just speaking IP, he has to speak Ethernet. It has to speak or Wi-Fi. They can't just speak a layer 3 protocol. You got to speak a layer 2 protocol. You've got to have a network interface card. Does that make sense, Rob? Switches are layer 2. And the funny thing is, they don't change your MAC address. Not a layer 2 switch. You could have a layer 3 switch, but if you have a layer 2 switch, they're just forwarding it. In fact, their basic job was to read the MAC address and go, hey, do I know where that MAC address is? Let me forward it just to the port that it's plugged in and not to all ports. So switches help control traffic from going everywhere. Cool. Jeremy's right. Switches are layer 2 and route traffic based on the MAC. So they were typically, when switches came out, since we're here, normally I bring it up later, but we'll just introduce now. Bridges came out, their job was to do one of 3 things: filter, forward, or flood. They all begin with an F. When I see a destination MAC address, I'm a switch. Right? I'll do a real simple one you can buy at Best Buy now, right? There's little switches here, and it's got whatever 8 ports. If this machine's plugged into port 1, he's going to learn his MAC address. He's going to look at the source MAC address and go, I learned this MAC on port 1. And then he learns Alice on port whatever 8. When Bob sends something to Alice, it says, oh, destination MAC address Alice, the switch will forward it to here, but it won't send it out the other ports. It filters it. So our 2 basic choices are forward or filter. But what if the destination MAC address isn't known yet? Or what if it's a broadcast address? It will flood it. It'll send it out every port except for the one it came in on. That'll help us lead to an attack later on. I just wanted you to consider flooding. So when it says, I don't know this destination MAC address, I'm going to send it everywhere. But since it came from here, came from 1, I don't have to send it to 1, but I'll send it everywhere else. Switches have grown. They do more than that now. But for now, that's what we basically think of a switch. Does that help? Cool. All right, so we're going to put devices that know how to read these things. By the way, we just pointed out a bridge works at layer 2. It knows how to read these things. A router can read packets. Actually, routers understand port numbers too. According to the RFCs, routers work here. They're called gateway to gateway protocols. They're not at the network layer or the there. On all tests that I've ever taken, with the exception of the CISSP, if you want to get the question right, and they say, what layer does a router work in? You always said the network layer. This test may say between what 2 layers. They know the truth. Not everything works neatly at a layer, between 3 and 4, that's right. Now, we're not seeing, because the TCP IP model didn't actually spec for a physical layer. So that's one of the advantages that came out with the OSI model. When we went to the OSI model, they got a little more granular. Right, so this is, now if you count, you can see layer 1, layer 2. So the data link, the link layer that we just saw before is actually what we would call 2. And routers are specified to work between 3 and 4. Another weird thing, I don't know where you guys are, we're going to see it. We're going to see ICMP. You may get beat up a bit on ICMP. ICMP, according to the RFCs, works here. But when you take most people's tests, you have to say ICMP is layer 3, routing is layer 3. Every practice test gets that wrong. Because people who write the practice test go, the IC square is wrong. No, they're not. They're right. Unfortunately, some people get involved in correcting the questions and think they're right. So I don't know. Some people tell me I didn't get any of the in-between Larrys. Remember you were telling me that? I didn't get any of that. But other people tell me they still do.